these were the two functions you're looking at once this comes up into view. Can we stop tapping, please? 31. So these are the two parent functions we looked at the other day. The reciprocal function is the first function graphed, 1 over x. And then we have the function 1 over x squared. And we noticed that for the vertical line, x equals 0, which is also the same thing as our y-axis, that this is our vertical asymptote. So that y-axis would actually be a dotted vertical line on both of these. And our horizontal asymptote for each of these was the x-axis, which is the line y equals 0. So we have our horizontal and our vertical asymptotes in each of these. They're both the same. The difference between these two functions is the first function has symmetry about the origin, so that for whatever x value I put in, if I take its opposite value, the y values are opposite what they are here. So the points here are in the first quadrant, which are positive, positive. The points to the left of 0 are in the third quadrant, which is negative, negative. This function, g of x equals 1 over x squared, has even symmetry about the y-axis. So as we take the opposite of an x value, the y value is exactly the same. That's even symmetry. So again, these were the ones that we worked on Friday, and we played all kinds of little transformation games with these. We shifted them to the right, up and down. Sometimes we did both types of shifts on them, and we got to play with these. So let's quickly do a review, and it's going to be quick, hopefully, so that we can get into today's material. We talked a little bit about vertical asymptotes the other day and a little bit about horizontal asymptotes. So how do we go about finding a vertical asymptote? What did we do? What was the process that we used to find the vertical asymptote? Ryan, do you remember? The vertex is for quadratic function. That's all right. Okay, so why is the vertical asymptote for both of these things the y-axis, which is the line x equals 0? Why is that the vertical asymptote? Yeah, Isabel? 0 is the excluded value, and how did you find the excluded value, Isabel? Why is it excluded? Right, so to get your vertical asymptote, you look at what values of the function make your denominator 0. So we set our denominator, which in this case is q of x, equal to 0, and we solve for x. And that's how we find the excluded values or our vertical asymptote. So we want to be concerned when we have a big fat 0 in the denominator. And this can happen for one value, no values, 2 values, 3 values. It depends on the function. Okay, and then we looked at the behavior of the function. That's the value of the function. It's class 31, Drew. The value of the function as we approach the vertical asymptote. And we talked about approaching the vertical asymptote from the right. And one of our choices when we approach an asymptote is we can grow without bound, we can blow up to positive infinity, or as we approach it from the right and the left, the value of our function can decrease without bound or approach negative infinity. So this is the summary of what happens as you approach a value of x that makes your denominator 0. As x approaches a being your vertical asymptote, x equals your vertical asymptote. From either the left or the right, the value of your function, your y value, is going to be getting really, really big or really small, approaching negative infinity or approaching negative infinity. In other words, an absolute value, it's approaching infinity. Okay. So how many vertical asymptotes can we have? So if we look, here's 3 different rational functions. How many vertical asymptotes are there in the very first picture here? Sean, how many vertical asymptotes there? This one right here. None, right. No vertical asymptotes. So that's always a possibility. What about the second picture, Tom? 1. And where is it? X equals 2. So does that look like one of your parent functions from Friday? Which one, Andy?
1 over function of x equals 1 over x.
1 over x, and it's been shifted right by 2. So how would I write that? I didn't give you the value of this function, but we can figure it out. How would I write it?
1 over x.
Perfect. There we go. Shifted to the right 2 units. All right. And then this function I gave you, but I didn't factor the denominator, but I could have, like this. There we go. And now we see how many asymptotes, vertical asymptotes do we have, Eliza? How many do we have? And where are they located? -2 and 2. And those are the 2 values that make our denominator 0. So we've just answered Q4. Can a rational function intersect a vertical asymptote? Can our graph cross it and have a value there? No, never, 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 ever, ever. So whatever taboo you learned, this is a big taboo. You can't have your graph cross a vertical asymptote, because if it did, if this crossed at x equals 2, that would say that I could put x equals 2 into this function and have a value for my function, and I can't, because 2 makes the denominator 0. So you never, never, ever cross your vertical asymptote. It's impossible. So how do we indicate the vertical asymptote? With a dotted vertical line. Okay. So this next part is the big part that's different in today's lecture, Q7. This is going to be the big part. So can you read this for us, Tom? Okay, stop right there. You might say, okay, geez, didn't I just learn about vertical asymptotes? I find a value or values of x that make my denominator 0. Boom, I go to my graph, draw a vertical line. Please don't change life on me. It's going to change in the next sentence. Go ahead, Tom.
Value where the denominator of a rational function is 0.
Stop. Oh, no. Why'd she have to change life on me? A value where the denominator of a rational function in 0 does not always result in a vertical asymptote. Well, what the heck is going on? Right? Someone moved your cheese. There was a poster once, right? Does anybody remember that Ziggy? Or remember there was a Ziggy poster where, oh, I remember this. Does anybody know who Ziggy is? Are you all too young for Ziggy? No, kind of like this kind of circular kind of figure. And he said, once I figured out where it was, someone moved it on me. So it's being moved here. All right, so something special is going to happen. There could be a value that makes your denominator 0, but it's not going to be a vertical asymptote. Then what the heck is going on? Continue, Tom.
The x value that makes the denominator 0 also.
Okay, stop there. It makes the denominator 0 and the numerator 0. So let's go back to the couple of functions we looked at. Here are the 2 functions we looked at. The value of x makes this denominator 0. Can it possibly make the numerator 0? And 1 over x? No, because the numerator is a constant. So the value of x here for both of these that made the denominator 0 couldn't possibly make the numerator 0. So yep, we're definitely in a new ballpark now. Then what does that mean?
Rational function as a whole at the x value rather than the vertical.
Okay, there we go. We have a hole in the graph at that value versus a vertical asymptote. So let's take a look at what's going on here. This also tells you that your rational expression is not reduced to lowest terms. Whenever you can find a value of x that when you plug it into your function, your numerator is 0 and your denominator is 0, it tells you it can be further reduced. So in this case, right here, we have a value of our denominator that makes it 0. It's -3. So when we write it into our factor form, x take away a -3 becomes x plus 3. So that tells you, when you say, the first thing you notice is that f of -3, if I plugged it into my function, would make my denominator 0. But don't stop there. Also plug it into your numerator. And if you do that, you notice that your numerator is also 0. So 0 divided by 0 does not represent any one number in the world. In fact, it represents an infinite number of numbers, because you could say 0 divided by 0 was -3,000 if you wanted. -3,000 times 0, 0. You can't, before, when we were doing this type of division by 0, we couldn't find one number in an infinite number set to define it. Now, with 0 divided by 0, there's an infinite number of possibilities. So that division can't be represented by one single number. So we can't do it. So when you have a situation like this, it tells you that that value of x, which then will correspond to a factor, is the common factor top and bottom. And you'll notice that you can factor this numerator, x plus 3, x minus 3, divided by x plus 3. And there you see it, the common factor that's both in the numerator and denominator. And this can be reduced further. This function can be reduced further. And lo and behold, instead of it looking like this crazy rational function, it looks like this simple function called x minus 3. What kind of graph would I get if I graphed x minus 3, f of x equals x minus 3? What kind of function is that? Linear. And now the only condition you have to put on this is that x can't be a -3, because -3 wasn't allowed in my original domain. So x minus 3 is what this function reduces to, but you have to put a little condition on it. You have to say x cannot be -3. So you can reduce this to lowest terms. And guess what, folks? That crazy looking thing is going to look just like this straight line. The y-intercept here is -3. And my slope is 1, so I go to the right one, up 1, right one, up 1, right one, up 1, right one, up 1. Here we go. Slope of 1, then down 1, to the left 1, down 1, to the left, ooh. Down left to the right, ooh. Right there's, I got to put an open circle. I have a hole, because what's the x value that goes right here? If I follow it up, my x value is -3. If I put a -3 into this function right here, -3 take away 3 is a -6. So that, instead of closing that point in, I have to put a hole there, because -3 is not allowed into this original function. And you connect all your dots with the straight line. So it looks just like the function f of x equals x minus 3, with one exception. This function is not defined for -3, and that's why we have this hole in our function. Okay. So you reduce your function, you graph it like you normally would, and then you take the value that's not allowed in the original domain, the excluded value, you plug it into your function, find the y value, and at that point you put a little hole. That's all you do. That's the only difference. In calculus, the name for this kind of hole is called removable discontinuity. That's a mouthful. We'll just call it a hole in the graph for Math 107. Okay. So that's the only new thing that you really need to know about graphing rational functions, is sometimes you can have these holes. Any questions before I move on? Ask now if you don't understand how we get a hole in our function. Anybody? I'm looking around. I don't see anybody like with glazed eyes. All right. Conclusions. Here's all your conclusions. Basically, your conclusions as you read through them tell you that X values that make a denominator equal to 0 can either result in a vertical asymptote or a hole in the graph, one or the other. You get a vertical asymptote when the X value makes a 0 just in the denominator, and you get a hole when the X value makes both your numerator and denominator 0. And the one little piece you can add to that is that tells you to do something. That tells you you can reduce your original function. You can reduce to lowest terms. It's not reduced right now. When you have that 0 in the top and bottom, it's not reduced, so continue to reduce it. All right, the end behavior of a function determines where or if it has a horizontal asymptote. This tends to be the most confusing part of rational functions for students, is this idea of a horizontal asymptote. Oh, by the way, Will, I did look up some applications for vertical asymptotes I can talk to you a little bit about afterwards. All right. So let's analyze the end behavior of a few rational functions and see if we can develop some conclusion. So those functions look kind of all the same if you peruse across there. What's different about them? How did I make changes? I didn't change the numbers. What did I change? As you look across A, B, and C, what did I change? The degree of the function on top. So notice in the first example, my numerator is 9x squared. So that's a little quadratic polynomial on the top. Its degree is 2. So what can you tell me about the degree of the numerator and the degree of the denominator here? Degree of numerator and degree of the denominator. What can you tell me about those two things? They're equal, right? The degree of the numerator is 2 and the degree of the denominator is 2. What about the second one, Chris? Can you tell me about what's happening between the degree of the numerator and denominator here? Okay, if we're just looking at the numerator, 9x, what would be the degree of that? 1. And if we just look at the denominator, what's the degree of that? 2. So how would you compare the degree of the numerator and denominator? Are they the same? They're different, right? And which one is bigger? Denominator. So the degree of the numerator is less than the degree of the denominator. Okay? So you try the next one again, since that was a little unfair. I hadn't give you any of that language for you to compare. So how about now? What would you say, Chris? Right, the degree of the numerator is higher or bigger than the degree of the denominator. So these are the three categories, folks, that you have to look at when you first look at a rational function. After you've taken care of whether or not it has vertical asymptotes, then you think about what happens to the value of my function as x gets really large in the right-hand direction or really small in the left-hand direction. Is there a horizontal line or a value that this function approaches? And if so, what is it? Well, if we look back at our parent functions, way back here, what would you say about the degree of the numerator and the degree of the denominator for both of those? Which one of those situations does it fall under? Is the degree of the numerator the same as the degree of the denominator in each of these? What's the degree of 1? No, it's not 1. 0, it's a constant. What's the degree in the denominator? 1. Is the degree of the numerator smaller or bigger than the degree of the denominator? Smaller. Which means what happens to this value as x gets really large? 1 over 1 is 1. 1 over 10 is a tenth. 1 over 100 is 100th. 1 over 1,000 is 1,000th. 1 over 1,000,000. I can't even draw my point. 1 over -1. 1 over -10. What happens to the value of my function as x gets large and as I move to the right, or small towards negative infinity as I move to the left? What happens to the value of the function? It decreases. It has to, because the denominator is getting bigger quicker than the numerator. It's decreasing and it's approaching a very special number. What's the number? What's the number this is getting close to? 0. It's the horizontal asymptote. So the same is true here, folks. It doesn't matter if I add all these, like, this stuff onto it. I have a first degree in the numerator, and my denominator is a second degree. Look at your horizontal asymptote. Look at what the value of this function is getting closer and closer to as x increases and as x decreases. It's getting close to the x-axis. And all you have to do is put some numbers into your calculator, like 10, 20, 50, 100, and you'll watch this fraction get closer and closer to 0. That will always happen. So as x approaches infinity, when your degree of your numerator is smaller than the degree of your denominator, your horizontal asymptote is the x-axis, y equals 0. It's right here. Always going to be true. When the degree of the numerator gets bigger quicker than the degree of your denominator, you have no vertical asymptote. Your function will go towards positive infinity as x, in this case, as x gets bigger, your function grows without bound, and as x gets smaller, your function decreases towards negative infinity. So if the top is bigger than the bottom, then there's no one number it approaches. We call this top heavy. This is top heavy. When you're bottom heavy, you approach your x-axis. Your value of your function is 0. So now the question is, what happens when you have the same degree top and bottom? Do I have a picture of that here? Not that one. There we go. So here are the three functions. I've got the first function, 9x squared over 3x squared plus x, graphed, just like you see, but I've also thrown in the horizontal line, y equals 3. And you can see that as x gets bigger and bigger here, and as I continue to get bigger and bigger, that the value of my function gets closer and closer to 3. If I spread this out, you see a little bit of a gap between the function, the graph of the function, and the line y equals 3. It's getting closer and closer and closer. And as x gets bigger and bigger, it's getting so close, it almost looks like it's exactly the same line. So the question is, how do I get let's take a picture of this. Well, you have a picture. How do I get this horizontal asymptote of 3 here? Let's look at this function, 9x squared over 3x squared plus 1. Let's throw this real quick into our calculator. And I want you to see how little effect this little baby plus 1 has on this function. So let's put the function in. Let's clear everything. God knows what I was doing a minute ago. All right, so here we got 9x squared, 9x squared divided by, first of all, let me put in 9x squared divided by 3x squared. 9x squared divided by 3x squared. What should I get for any value of x? 9x squared divided by 3x squared. No matter what x I put in. Go ahead, say it. 3. 9x squared divided by 3x squared. What happens to the x squared over x squared? Cancels. What's that become when you say it cancels? What number? What number? Come on, folks. 9x squared divided by 3x squared. X squared over x squared cancels. What number does it become? 1. So what's the only numbers we have left? 9 divided by 3, which is what? 3. What's my horizontal asymptote here? 3. And you know why? Because once I throw in this little, so let me show you this as a table. So I'm going to start off with the number 4, and I'm going to ask my table to give me the value. And no matter what number I put in here, 3, 3, 3, 3, 3, all the way down. So let's see what happens when I actually plot the function that's there. I'm going to plot the function that looks almost the same, except I'm going to add a little 1 in the denominator. So let's do the same thing. I'm going to start with a number like 4. And I'm going to go down and ask my table here to tell me the value of my function for different numbers as x gets big. Well, let's see what it is at 4. At 4, it's 2.9388. Okay, it's close to 3. How about at 10? 2.99, getting closer to 3. What about as x goes way out? Let's put 1,000 in here. It's going to give me 3. It's not exactly 3. It's 2.9999. I just don't have this out as many places as I need for you to see it. It just rounded it to 3. What about the other direction? What kind of symmetry does this have? Kind of symmetry. Y-axis symmetry. So when I put a negative 4 in, what should be my value? Exactly the same as for positive 4. Right? When I put in 1,000, I should get 3 back again. So the moral of the story, folks, is even if I had a little 2 plus 2x plus 1 there, when x is getting really, really big and it's growing in the numerator at the same rate as it is in the denominator, your degrees are the same, this little auxiliary stuff here, the little stuff added on, has very little effect in the overall value of the function. It's almost as if it's not there. And what you're really looking at is 9x squared over 3x squared, which reduces to what? 3. You just literally take the leading coefficient in the numerator and divide it by the leading coefficient in the denominator. So that's your horizontal asymptote, is 3 for this particular function. So all that's written here in your conclusions. I wrote it somewhere. Here it is. That's all written here in your conclusion. And so let's start graphing some rational functions so that you can have time to do it. So here's my first rational function. Where do you start? Well, make sure it's fully reduced. Before I even do that, I'm going to call this step 1.5. I got to find the domain. That should be the first thing I do. Find the domain, always. All right. So what's the domain of this function? Drew, help me with the domain. How am I going to find the domain? Drew? Pass. Anybody else? Find the domain? Dylan? That would be for that horizontal. No, look, it's fine. That would be for the horizontal asymptote. The domain is what numbers are allowed to go into this function. Are there any excluded numbers here? Pat? Right, the domain here is all numbers except for 3 and negative 3. It's a set of all numbers x except for 3 and negative 3. And how did Pat get that? How did he get the 3 and the negative 3? He did something in his head. Yeah, he looked, to get the domain, we have to worry about what values of x will run into trouble here. And in this case, it's what values of x is going to make my denominator equal to 0. That's what I have to figure out. Again, I encourage you to factor this instead of saying x squared equals 9 because you'll forget plus and minus. But hopefully by now, with all the work we did with polynomials, you know that this equation has 2 zeros. In this case, they're both real numbers. X equals 3 and x equals negative 3. And you can get that by factoring this and seeing both factors are different, and therefore we have 2 different zeros. So that's how I get the domain. That's also what leads me, these are equations. That leads me to vertical lines. X equals 3 and x equals negative 3 are vertical lines. So that's my vertical asymptotes. I can start with putting these dotted vertical lines straight down through positive 3 and negative 3. Now, this is not part of my graph. This is just an aid to help me graph my function and see what happens to the behavior of it as it gets close. All right, now. So that's kind of step 1, finding the domain. When you find the domain, you find the excluded values. The excluded values are going to lead you right down to number 5, which is your vertical asymptotes. Boom, right away. You get to see that part of your graph. Okay. So now I have to determine if I have any kind of symmetry. And why does that help me? Because if I have even symmetry, all I have to do is draw half of my graph, either the half of the graph to the right of the y-axis or the half of the graph to the left of the y-axis, because they're mirror reflections of each other. Or if it has origin symmetry, same thing. I draw half the graph and then I reflect it over the origin. So here's f of x. What does f of negative x look like? What would f of negative x look like? That means everywhere I see an x, I replace it with negative x. And guess what? It comes out looking exactly the same as f of x. So this tells me I have y-axis symmetry or even symmetry. So that's great news because I only have to do half the work now. So I have even symmetry or y-axis symmetry. So I can circle that up here. Cool. Done that step. Find the y-intercept. To find the y-intercept, I evaluate my function when x is 0. So I put 2 times 0 square over 0 square minus 9. That's 0 over negative 9, which is 0. So 0, 0 is my y-intercept. And now my x-intercept, if any. My x-intercept, I only have to be concerned with the numerator equaling 0, because when I have a fraction, the only way the value of my fraction can be 0 is when the numerator is 0. So I set my numerator equal to 0, and guess what? It's exactly the same x value as my y-intercept. So my origin here is going to be an important point. It's acting as both my y-intercept and my x-intercept. Okay, now it's the idea for the horizontal asymptote. This is what Dylan was talking about. The degree of the top and bottom is the same. So literally, you can ignore anything after the x square. And the denominator doesn't matter what comes after it. And now you're looking at 2x squared divided by 1x squared. As Caitlin said, the x squares cancel. So your horizontal asymptote here is just y equals 2 divided by 1. You take the leading coefficients, and that gives you a 2. So now I'm going to start out here somewhere and just do a dotted line at y equals 2 like this. Dotted line at y equals 2. And I'm not going to, sometimes you learn to put that dotted line all the way across, but I'm just going to keep it like that. You could put it all the way across like this if you wanted to. I don't, because I just don't do it. I just kind of put it up to and really close to both of my vertical asymptotes. And the other reason is because what is my horizontal asymptote? It's the value of your function when you're way out here. I'm stretching my arms out, all right? That's what I want to know, way out here. Not like in here around 0 and -3 and positive. It's way out. That's your end behavior, what the value of your function looks like. So you know what? You're ready to go, folks, believe it or not. Now, this is the way the book leads you. I'm going to kind of give you how to graph these, but by looking at each tree in the forest. At the same time, I'm going to tell you how to graph it by looking at the forest from a bird's eye view. It's kind of the conceptual idea that you've learned when we were dealing with polynomial functions. So I'm going to give you both. Okay, plot at least one point between and beyond each x-intercept and vertical asymptote. Okay, so we have one x-intercept and we have 2 vertical asymptotes. So right now, just focus on the x-axis. How many pieces has this x-axis been broken up to? If you look at where your vertical asymptotes are and where your x-intercept is, how many actual individual pieces do you see there? If you just look at just the horizontal line called your x-intercept, your x-axis. How many chunks is it broken up into, Katie? And how would you describe those 4 pieces with interval notation? Right, here's my first. If I go to the left of this vertical asymptote, I have one part of my graph that's going to have a certain behavior. So I'm going to call that the first part of my graph, or interval 1. It says between your vertical asymptotes and your x-intercept. So where's the next part of my graph going to be, the next interval, if I go between my vertical asymptotes and my x-intercept? In interval notation, can someone tell me where that interval is? 3 to 0 over here? Here? Oh, -3 to 0, right. So that's my next interval right in there. So that's, I can pick an x value in there. X-intercept to my next vertical asymptote would be what interval? 0 to 3. And then finally, my vertical asymptote and beyond? Toy Story? Yeah, 3 to infinity. So all you need to do now is pick a value in each one of those intervals. Here's my first interval, -infinity to -3. That's interval 1. Here's my second interval, -3 to my x-intercept, 0. Here's my third interval, 0 to +3. And here's my fourth interval, 3 to infinity. And all you have to do is pick a value of x in that interval. And all you want to do is say, is the value of my function on that entire interval? Because once you have one number in that interval, all the other numbers in the interval behave in a similar manner. So is the value of my function in that interval positive or negative? That's all you want to determine. So I'm going to start on the right here. I'm going to pick a number in interval number 4, a number that's bigger than 3 and goes towards positive infinity. Anybody got a number they want to pick in this interval right here? 5. Okay, so let's determine f of 5. All I'm determining is whether it's positive or negative, the value of my function. So I put a 5 into my function. Let's take a look at what my function was again. I put a 5 into the numerator. Am I positive or negative if I square 5 and double it? Positive or negative? Positive, okay? What about my denominator? I square 5 and I subtract 9 from it. Positive. So I got a positive divided by a positive. That makes me pretty darn positive. So to graph this part of my function, when I'm way out here, I'm hugging that horizontal line y equals 2. And I'm going to hug it. Hug it, hug it, hug it. And as I get close to my vertical asymptote, I go up to positive infinity because that's what this tells me to do. I'm always going to be positive. That means that this part of my graph is above my x-axis, but because I have this horizontal asymptote, that graph is going to look like this. All right. Now, here's the part that has to do with seeing the forest from a bird's eye point of view versus what we're going to do next. And I'll show you both ways. Oops. I'm going to factor this for you again. Okay, each of these factors has an odd multiplicity of 1. This factor is 0 at 3, and that's represented by this blue dotted line right here. At an odd multiplicity, what happens to the sign of your function? When we were looking at polynomial functions, we would be looking at an x-intercept right now. At an odd multiplicity, what happens to the value of the function as you go from one side of your x-intercept to the other side? What happens to the value of your function, to the sign of your function? It changes from positive to negative. So right now I'm on the right-hand side of 3 and I'm working my way up to positive infinity. When I take a little teeny weeny baby step to the left of 3, what's going to happen to the value of my function? It's going to change sign and it's going to come down here. And I'm going to hug, 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 and I'm going to move my way up towards that x-intercept. That's what's going to happen to me. Now you say, what if I didn't think of doing that, Linda? Fine. Pick a number. In this interval, all you want to know is what's the value of your function? Is the value of your function up here or down here? So pick a value of your function, your favorite number between 0 and 3. If your name is not Will, what number would you like to pick? 2. Let's put f of 2 in. So I get 2 times 2 squared, that's positive in the numerator. 2 squared minus 9 is negative in the denominator. That means my value of my function, if I pick any number in this interval, the value of my function is negative. That's what it tells me. You don't have to plot point by point like you did way back in introductory algebra. And you know that you're hugging this and you're going to approach this until you get to 0, 0. Now, this is where symmetry comes in. It saves you all of the next steps. This function has even symmetry, which means if I literally folded this function over the y-axis, I'm done. So here it's going to come right back down because it's going to be a mirror image of what's between 0 and 3, and 0 and negative 3 are going to be mirror images of each other. And to the left of negative 3 is going to be a mirror image of the graph to the right of 3. You are done. There you go. Just put your little arrows. But again, until you feel confident about that, you can pick values in each of these intervals. So if I now pick negative 2, my numerator is positive, my denominator is still negative. That tells me I start here and I go down and hug my vertical asymptote. Then notice something, folks. Here's where your vertical asymptote is at x equals negative 3. You have an odd multiplicity. You know your sign of your function has to change from negative infinity to positive, and then you just hug your horizontal asymptote. That's all you're doing. You're sketching this. You're not getting exact values for points. You're just sketching its behavior. That puts together a lot of ideas from polynomial functions, and now these new ideas with rational functions. I'm going to do one more for you, and then you're going to have the whole rest of the class to practice this on your own. Here's the next one. Find the domain. Okay, so hopefully after the first one, how do I find the domain? And then find the excluded values so I can get my x, my vertical asymptotes. How do I find the domain here, Christopher? Yeah, I want to set the denominator equal to 0. It's a quadratic function, so how many zeros will I have? 2, always 2. And if I factor this, I see both of them, -1 and +1. So those are my 2 vertical asymptotes. Boom, I put my vertical line straight down through -1, and boom, how'd that happen? Boom, straight down through +1. There we go. So my domain is the set of all x such that x does not equal plus or minus 1. And there are my 2 vertical asymptotes, the equations for them. Okay. Now, do I have even symmetry or odd symmetry, or neither? Well, let's see. Here's f of x, 4x over x squared minus 1. The minute I put the opposite of x in, I automatically see my top is going to be negative, and that's not equal to f of x. So I don't have even symmetry. When I put it in on the bottom, my denominator is the same. So what that tells me is that f of negative x is the opposite of f of x. Because if I want to take the opposite of a fraction, I make either the numerator the opposite or the denominator. Or I put the dash out in front of the whole thing. So if I make the top negative, it looks just like f of negative x. So this is going to have origin symmetry. Again, once I get the graph from 0 to the right or 0 to the left, then I just have to do a reflection twice. Or that's how you get origin symmetry. All right. So what do I have to do? Yep. Sure. Yep.
Finding out, are you just putting negative x for x?
Yep.
But in the top half.
If I have a fraction like this and I want its opposite, how can I write its opposite, Katie? Where you want me to put it? Front of it? Where else can I put it? On top? Where else can I put it? Of course. If you have a fraction and you want to change its sign, you can change either the numerator or the, because look, it's negative divided by, oops, I shouldn't say equals. These aren't equal. So here you got a positive divided by a positive. You can either say, I'm going to change it by putting the negative out front of the whole thing, saying negative 1/2, or you can say, to get a negative fraction, I either make my numerator negative and keep my denominator positive, or vice versa. So here, when you put in negative x, it makes your numerator negative 4x, but your denominator stays the same because negative x squared becomes x squared. So this has origin symmetry. All right, so let me erase that. Yep, Caitlin?
If you were to decide to change the denominator to wait, never mind.
I have to put negative x in everywhere I see x. So my numerator is still going to be negative 4x, but my denominator, when I put negative x in, looks like this, which is the same as x squared. Okay? Nope. All I was saying is that if the sign of the top or the bottom changes to the opposite, then the whole thing is the opposite. All right. Any clarity on how to make a fraction opposite? I mean, any more questions? I hope that was a little clearer. Okay. So now what else do we need to do? We have to find our intercepts. So our y-intercept is when x equals 0. That's 0 over -1, which is 0. So that means my origin is going to be my y-intercept. And my x-intercept, or intercepts, is all I have to do to find that is pick on my numerator and set my numerator equal to 0. Because when the numerator of a fraction is 0, the whole thing is 0. So when does 4x equal 0? When x is 0. So again, my origin is playing a double role here. Okay, it's both the y-intercept and the x-intercept. Now we have our horizontal asymptote, which is y equals 0 in this case, because the denominator is growing faster than my numerator. So my x-axis is now acting as my horizontal asymptote. So as the value of x gets close to positive infinity or negative infinity, my function is going to be approaching my x-axis. So where do I go from here? You still have your intervals here. Your first interval is from negative infinity up to -1. That's interval number 1 if you want to pick a value from that interval and see where the value of your function is. Then you have from -1 to 0, that's your second interval. From 0 to your other intercept, your vertical asymptote, sorry, and then out here. Or you could try to see the forest through the trees, which is what I'm going to do for you right now. I'm going to factor this. We have 4x over x plus 1, x minus 1. So I'm going to go start way out here on the right-hand side of my graph. And as x is really, really big, I have to determine, I know I'm going to be hugging the x-axis, but am I going to be above it or below it? That's all I have to ask. Am I positive or negative? So I just pick a value in this interval, any number. Let's put in 5, f of 5. My top is positive, my bottom is positive. So that tells me I'm above the x-axis. And as I approach, I'm going to hug my horizontal asymptote. And as I approach my vertical asymptote, I shoot up to positive infinity. That's all I have to do. I don't have to be concerned about exactly where I'm crossing here. I'm just sketching. So I've taken care of my first interval. Now, if you want to know what's happening between 0 and 1, pick a number between 0 and 1, like a half. 4 times a half is positive. 1/2 squared minus 1 is negative. So that tells you you're below the x-axis. But guess what? You would have known that by looking at this multiplicity at x equals 1. Because it's odd multiplicity, when you take your step over, you're down at negative infinity. So you're coming up here. And you bend right as you go there. Now, You have origin symmetry, folks. This is not going to come back down like this. Now, as you change your x values from positive to negative with origin symmetry, your y values will go from being negative to positive. Or you could pick a number in between here, like negative 1/2, and you would get a negative over a negative, which is positive when you put it in your function. So this is going to go up like this. And now, similarly, at negative, when x is -1, you're at this vertical asymptote. Here's your odd multiplicity. Your sign of your function is going to change from positive down here. So you're going to hug this asymptote and hug it all the way out to -infinity. Again, you can see that this graph from 0 to 10, in this particular case, looks identical. Excuse me, the graph to the left is the opposite. So if this was negative, this is positive. This is positive, this is negative. That's your origin symmetry. But again, if you still aren't comfortable there, pick a number in this interval like -5. 4 times -5 is going to give you a negative in the top. -5 squared minus 1 gives you a positive in the denominator. The whole function is negative. You're below the x-axis. Katie? No, the origin is an actual value because the holes are at 1 and -1. It's okay for x to be 0. So if I put a 0 in here, I get 0 in the numerator and I get -1 in the denominator. 4 times 0 over 1 times -1 is 0 over -1, which is 0. It's what makes my numerator 0. Okay, which is okay to have a 0 upstairs. Right? So those are the two functions. You have 9 rational functions to graph. You are not going to get them all done today. I would suggest by Friday you make sure you have them all done. Okay, so get as many done today or look them over. Start with one you think will be the hardest for you to do while you have your classmates and me available to you for the next 20 minutes or so. Yep. No, not my horizontal asymptote. My horizontal asymptote is done by looking at the degrees of my numerator and denominator. So my numerator has a degree of 1 and my denominator is a degree of 0. So I think back to one of my rational functions, 1 over x or 1 over x squared. When the degree of my denominator is bigger, my bottom, this is a bottom heavy one, my function's value is always going to approach 0 as x gets really, always 0. If the bottom is heavy, yes, always 0. Any other questions? Yeah, Andy?
The end behavior, the right end behavior.
The right end behavior over here, yeah. Yeah.
You determine that it's positive.
By just picking any number in this interval.
Because there's positive and positive. And that's how you know.
That's right. Like here, I put a 5 in, and my numerator is positive, my denominator. So that means my whole function's positive, so I'm above the x-axis. Okay? You have pencils in your toolkits for different colors to help you graph. You have me, you have your table mates. Please ask questions if you have them. I'll be glad to help you.